Have you ever stared into the night sky and wondered whether the stars were watching you back? Whether beyond the quiet shimmer of starlight, something vaster, something deeper was unfolding. We often think of space as cold, distant, and silent, but it is also a stage for the most dramatic forces the universe has ever known. And of all the characters that roam this cosmic theater, none are more enigmatic, more feared, and more fascinating than black holes. This journey begins not at the edge of the universe, but at its center, at the very boundaries of our understanding. Because what if everything we see, everything we are, is not outside looking in, but inside looking out? What if we ourselves live not in a universe expanding into nothingness, but inside a vast, spinning black hole? That idea, once whispered at the fringes of science, has returned with new fire. And to understand why, we must first understand the nature of black holes themselves. Through the event horizon, entering the dark heart of the cosmos. Not the pull you feel when you drop a stone or the quiet force that keeps your feet planted to the ground, but a cosmic curvature of space-time itself, a dance between mass and geometry. The story of black holes starts where mass becomes so concentrated that space buckles and time itself begins to lose meaning. When massive stars reach the end of their lives, their outward pressure, driven by nuclear fusion, can no longer counteract gravity. The core collapses, and if the mass is high enough, it collapses all the way and past white dwarfs, past neutron stars, into something far stranger, a singularity, a point of infinite density wrapped inside an event horizon beyond which not even light can escape. From the outside, this event horizon looks like a dark sphere floating in space. But what lies beyond it? What happens to matter, time, and space inside this abyss? It's a question that has haunted scientists, philosophers, and storytellers alike. We used to think of black holes as monsters, cosmic vacuums devouring everything nearby, but the truth is subtler. Black holes aren't hungry. They don't pull things in with magical force fields. Instead, they simply exist where the geometry of space has folded so tightly that all paths lead inward. If you pass the horizon, you're not sucked in. You're simply moving forward, and in a black hole, forward means deeper. That brings us to the thought-provoking idea that kicked off this journey. What if that downward spiral doesn't end in destruction, but in rebirth? What if the singularity isn't the end of the road, but a gateway, a bounce, a transition? In black hole cosmology, our universe, the stars, galaxies, cosmic background, radiation, everything may be the inside of a black hole that formed in some larger parent universe. To wrap your head around this, imagine a Russian nesting doll of realities, a cosmos within a cosmos, spinning silently in the dark. Our Big Bang wasn't an explosion from nothing, but the rebound of matter compressed past its limit in a parent universe. The singularity never formed. Instead, space and time were twisted so tightly they rebounded outward, creating what we see today as cosmic expansion. And the place we call the beginning may actually be the other side of a one-way cosmic doorway. In 1915, he introduced general relativity, the astonishing realization that gravity is not a force, but the result of curved space-time. Mass tells space how to bend, space tells matter how to move. And in the equations of relativity, something unexpected emerged: black holes. But Einstein himself was skeptical of them. The singularities predicted by his theory seemed too extreme, too unphysical. He believed the math must be hiding some deeper truth. Today, we still wrestle with that. Because while general relativity tells us how black holes should behave, it doesn't tell us what happens inside them. That's where we reach the limits of our current understanding, where quantum mechanics and relativity clash and where something new must emerge. Let's return to the event horizon, the boundary beyond which nothing escapes. From the outside, time appears to slow as an object approaches this line. You'd never see it cross. It would simply freeze, fade, and vanish. But for the object falling in time marches forward. There is no wall, no moment of contact. Just the inescapable geometry of space-time funneling you inward, and the question remains, inward to what? Some theories suggest the center is a singularity. Others, like the Einstein-Cartan theory, propose that quantum effects, specifically the intrinsic spin of particles, create a repulsive force at extreme densities. Instead of crushing to a point, the matter rebounds. And that rebound might be a Big Bang. There's more than one kind of black hole. Stellar black holes form from dying stars and range from a few to dozens of solar masses. Intermediate mass black holes, a missing link suspected but not often confirmed, may form from the merger of many stellar black holes or the collapse of dense gas clouds. And then there are supermassive black holes, monsters millions or billions of times the mass of our Sun, found at the centers of galaxies, including our own. How do these behemoths form? No one knows for sure, but the fact that they exist and influence the very structure of galaxies tells us they are not anomalies, they are essential. And finally, we have the theoretical primordial black holes, possibly born in the early universe if they exist at all. Some theories even propose that dark matter might be primordial black holes. If so, black holes didn't just come after the Big Bang, they may have preceded it. Wormholes, those famous science fiction shortcuts, emerge naturally from the equations of relativity. A non-traversable Einstein-Rosen bridge connects two points in space-time, like the entrance and exit of a tunnel. In black hole cosmology, that tunnel leads from the parent universe into ours. Could such a wormhole ever be crossed? Probably not unless negative mass exists, a strange form of matter that exerts anti-gravity. We've never observed it, but the universe hasn't ruled it out either. If such matter exists, it might make it possible to survive the journey. And if advanced civilizations exist, ones that have reached Type 3 on the Kardashev scale, harnessing the energy of entire galaxies, might they have learned how to create their own black hole universes? Might they live in custom-made realities beyond our reach and comprehension? It's speculative, but it's also profoundly exciting. As we move forward in this journey, the questions deepen. What did the James Webb Space Telescope see that reignited this idea? Why do some galaxies appear to rotate preferentially in one direction? How does this tie into the structure of our universe and the idea that it too might be spinning? In the next section, we'll explore the rotating black hole universe theory, what it is, where it came from, and why recent observations have given it new life. But for now, take a moment to consider this. If the universe truly is a black hole, then every time we look up at the stars, we're not looking out, we're looking in. Spinning realities. A universe born in rotation. We ended the last chapter with a striking idea that we may not be looking out into space, but rather into the interior of a cosmic engine, an immense, rotating black hole. If that sounds extraordinary, that's because it is. But the story doesn't end with that image. It begins there. The question is no longer simply whether black holes can birth universes. It's more precise now. Could our universe, with its stars, its symmetry, its silence, and its noise, have been born spinning inside a rotating black hole? To understand why this matters and how it fits together, we need to explore a theory that has moved from the sidelines of cosmology toward the center of serious discussion, the rotating black hole universe model. A bold extension of black hole cosmology that reinterprets the very origin of everything we know. In standard cosmology, the Big Bang is a singular event, an explosion of space itself from a hot, dense point some 138 billion years ago. From that first moment, the universe expanded rapidly, then cooled, forming atoms, stars, galaxies, and life. But for all its success in explaining observations, this model leaves some essential questions unanswered. Why did the Big Bang happen? What came before it? Why does the universe appear so finely balanced, flat, smooth, and structured? In black hole cosmology, the beginning is not a singularity in the traditional sense, but rather a bounce, a collapse, followed by expansion. And in the rotating variant of this model, it's more than a bounce, it's a spin-up. The parent black hole that birthed our universe wasn't static, it was rotating, and so are we. This theory builds on the idea that a black hole can carry angular momentum. In the language of relativity, this is known as a Kerr black hole, a rotating solution to Einstein's field equations first described in 1963. Unlike a simple Schwarzschild black hole, which doesn't rotate, a Kerr black hole twists spacetime as it spins, dragging nearby matter, and even light around with it, a phenomenon called frame dragging. Now imagine that this spinning black hole doesn't just exist in isolation. Imagine that within it, a universe is forming, a universe born with rotation embedded into the very structure of its spacetime. In 2023, the James Webb Space Telescope, JWST, captured images of distant early galaxies. These galaxies, among the first to form after the Big Bang, showed something strange. A preference in rotation. Approximately 2/3 were spinning clockwise. Only 1/3 spun counterclockwise. This wasn't what we expected. In a universe formed by random processes, we'd anticipate an even split. Galaxies should rotate in both directions equally like coins flipped by chance across the cosmos. But here was a statistical imbalance, a subtle yet significant hint that something about our universe had a preferred direction. Physicist Leor Shamir analyzed over 260 galaxies and found this discrepancy. While it has yet to be confirmed by other surveys, and some suggest selection bias may be to blame, the mere possibility has sparked renewed interest in black hole cosmology. Because if the universe was born inside a rotating black hole, then this preferred spin might not be an accident. It might be a signature embedded in the galaxies themselves. Let's zoom out both figuratively and literally. In the Kerr solution, rotation has profound effects. Not only does it alter the geometry of spacetime, but it also changes the causal structure of the black hole. Unlike non-rotating black holes, Kerr, black holes contain an inner horizon, an ergosphere, and potentially even a passage through to another region of spacetime. From a cosmological perspective, rotation provides several fascinating advantages. A rotating black hole universe generates natural anisotropy, a slight departure from perfect symmetry, just like what we observe in the cosmic microwave background, CMB. Predicts a direction of time. The spin defines an arrow, possibly linking to the thermodynamic arrow of time we experience. Offers an internal engine. The centrifugal effects of rotation can counterbalance gravitational collapse, enabling the bounce that prevents a singularity. And here's where the connection gets eerie. The mathematics of such a rotating bounce generate conditions that closely mimic cosmic inflation, the rapid expansion theorized to occur in the early universe. In the standard model, inflation is added to solve problems like flatness, homogeneity, and the horizon problem. But in black hole cosmology, inflation emerges naturally from the dynamics of rotation and collapse. That's not a patch, that's a prediction. If our universe is the interior of a rotating black hole, what does that make the event horizon? From our side, it's the observable edge of the universe. But from the outside, in the hypothetical parent universe, it's a black hole's outer boundary cloaking a strange interior. And if the collapse didn't end in a singularity, but instead led to a bounce, then the matter that fell inward never stopped. It rebounded outward through what's called an Einstein-Rosen bridge, a non-traversable wormhole that connects two regions of space-time. Each black hole becomes a cosmic womb, birthing a new universe. Each new universe begins with its own laws, structures, and dimensions, but perhaps carries echoes of its origin encoded in its rotation, its geometry, and its quantum state. In this framework, our universe is a child, but it, too, may become a parent. Every black hole within our cosmos could harbor another universe beyond its own event horizon. It's a fractal vision of existence, universes within universes, each one spinning, evolving, birthing new realities beyond the grasp of the last. This leads to one of the most poetic and most haunting questions in cosmology. If our universe was born from a black hole in another universe, then where did that parent universe come from? And what about its parent? Does this chain continue forever? Are we just one in a potentially infinite hierarchy of embedded realities? And if so, is there an origin, a primordial universe, a first black hole? Or is it really turtles all the way down? We don't know. And that not knowing is part of what makes this theory so beautiful, because in exploring it, we're not just asking about equations and energy, we're asking about meaning, about place, and about the strange possibility that the truest boundaries of our universe are not distant galaxies, but the curved walls of a cosmic interior. Let's add one last speculative layer. If this theory holds and black holes birth new universes, then perhaps sufficiently advanced civilizations, those that reach Type 3 on the Kardashev scale, don't simply master energy, they master creation. They could, in theory, collapse matter in a controlled way to form artificial black holes, seeding new universes. Not as weapons, not as experiments, but as refuges. What if the solution to the Fermi paradox, the question of why we don't see evidence of alien life, is simply this: the most advanced beings have left. They've migrated into universes of their own design, universes better suited to their existence, universes they control from the inside. And we're the ones who stayed or were born here long after the architects had gone. It's a chilling, humbling possibility, but not a hopeless one, because it means that intelligence doesn't disappear. It evolves in ways we cannot yet comprehend. In the next section, we'll compare the rotating black hole cosmology model to the standard Big Bang model and ask where each excels, where they falter, and what new light they cast on the mysteries of inflation, dark energy, and cosmic structure. But already one thing is clear: this theory doesn't just reshape how we think about black holes. It reshapes how we think about the entire universe. Maybe we were never meant to escape black holes. Maybe we were born in one. Two origins, one universe, a tale of two cosmologies. So far, we've journeyed through the core ideas behind rotating black hole cosmology, a universe born not from a single explosive point, but from a collapse, a bounce, and a spin. But before we get swept up in the poetic allure of this alternative model, we must step back and ask, how does it compare with the reigning paradigm? The standard model of cosmology built upon the Big Bang theory has withstood the test of time for nearly a century. It describes an expanding universe that emerged from a hot, dense state predicted by general relativity and supported by a wealth of observational evidence. The cosmic microwave background, CMB, the abundance of light elements, the large-scale structure of galaxies, and the redshift distance relationship discovered by Hubble. So why challenge it? What gaps remain in the Big Bang story that invite other voices, like black hole cosmology, into the conversation? Let's explore the contrasts between the two. He's standard model posits a singular origin, a moment of infinite density and temperature from which everything emerged. It does not, however, explain why the Big Bang happened or what came before it. At T0, our equations break down. Time itself ceases to have meaning. It is quite literally the edge of understanding. In black hole cosmology, there is no such absolute beginning. Instead, the birth of our universe is interpreted as the interior evolution of a black hole formed in another universe. This is a bounce, not a beginning, an unfolding of compressed matter into a new cosmic arena. In this model, time doesn't start. It continues, or albeit in a radically different form. One story starts from nothing, the other from something else. One of the most successful additions to the standard model is cosmic inflation, a burst of exponential expansion in the first fraction of a second after the Big Bang. This idea explains three big puzzles. Why is the universe so flat? Why is it homogeneous across vast distances? Why do distant regions have identical temperatures even though they've never been in contact? Inflation solves these problems, but at a cost. It introduces a new energy field, a new particle, the inflaton, and parameters that must be finely tuned. By contrast, rotating black hole cosmology achieves similar results without adding new ingredients. The geometry of a rotating collapse, curved space-time under torsion, naturally produces an inflation-like expansion during the bounce. In this framework, inflation isn't added on, it's built in. That elegance is seductive, but it must still be tested. Time is perhaps the most mysterious dimension we experience. In both models, the universe expands with time, but their treatment of time's origin is different. In standard cosmology, the arrow of time, the reason events unfold in one direction, is explained through entropy. The early universe was in a low entropy state, and entropy has increased ever since. But why did it start that way? Black hole cosmology offers a different lens. If our universe is the interior of a rotating black hole, then the arrow of time might be inherited from the parent universe. The spin and structure of the parent define the orientation of causality in the child. Time has a direction, not because of chance, but because of cosmic heritage. Both models agree that the CMB is a critical test. In the standard model, the CMB is the relic radiation from the hot plasma of the early universe, cooled to 27 K today and astonishingly uniform. Tiny variations in temperature on the order of microkelvin reveal the seeds of all structure in the cosmos. Black hole cosmology interprets these variations as signatures of the bounce and rotation. For instance, subtle asymmetries in the CMB polarization could indicate a preferred spin direction inherited from the black hole that birthed our cosmos. Recent high-precision data from Planck and other missions have found anomalies, dipoles, cold spots, alignment of multipoles that don't fit neatly into standard predictions. They don't prove black hole cosmology, but they whisper that something more may be at work. In the standard model, the accelerated expansion of the universe is driven by dark energy, a mysterious component that makes up about 70% of the cosmos. We know it exists. We don't know what it is. In black hole cosmology, this acceleration is a natural consequence of being inside a rotating, growing black hole. As mass continues to fall into the parent black hole, the volume of the interior universe grows. No extra field required, just a different point of view. It's as though our cosmos is inflating from the inside, not from an exotic vacuum energy, but from the continuing infall of matter in the higher dimensional world outside. Does this mean black hole cosmology wins? No, not yet. The standard model remains unmatched in its precision and predictive power, but it leaves open doors, questions it cannot answer, patterns it cannot explain. Rotating black hole cosmology doesn't close those doors. It steps through them and finds something waiting on the other side. A universe not just expanding but evolving through cosmic inheritance. A universe not born in isolation but part of a vast, possibly eternal chain of black holes and baby universes. It's bold, it's speculative, but it just might be true. Shadows and signals. Can we prove the black hole universe? We've walked the line between two grand visions of cosmic origin, the classical Big Bang and the bold elegance of black hole cosmology. The latter reinterprets the observable universe as the interior of a vast rotating black hole, its expansion structure and direction shaped by inherited properties from a parent universe. And it's compelling seductively so. But science doesn't thrive on poetry alone. It breathes through evidence. So we must now confront the uncomfortable question, how do we test this? How do we distinguish between metaphysical speculation and scientific reality? How do we look for the fingerprints of a parent universe from within the walls of our own? The path forward isn't smooth, but it is navigable. In 2016, a strange idea began to circulate in gravitational wave research. LIGO, which had recently detected the collision of black holes, a triumph in itself, had also registered anomalous echoes in the aftermath of some events. These faint delayed repetitions of the initial signal sparked whispers of something exotic, perhaps quantum structure at the edge of black holes, or even evidence that what we call a black hole might be more complex. Within the black hole cosmology framework, these echoes become something more. They might be reflections from the boundary of the universe itself, a sign that our cosmic horizon isn't just a limit of our view, but a real physical edge. A membrane, a wall. If that's true, then we're not just receiving whispers from dead stars. We're hearing the rumble of our cosmic container reverberations from the curvature of a larger dimensional reality. Still, critics rightly urge caution. These echoes are weak. Controversial, not universally observed. The signal could easily be noise, and multiple follow-up studies have failed to replicate the findings consistently. But like a knock in the dark once heard, it's hard to ignore. We explored one of the most fascinating and polarizing observations from the James Webb Space Telescope, a disparity in galactic rotation. According to physicist Leor Shamir's analysis, early galaxies appear to spin with a directional bias. Roughly 2/3 rotate clockwise, and only 1/3 counterclockwise. This imbalance isn't predicted by standard cosmology. In fact, it should be impossible if the universe had no preferred direction at birth. To black hole cosmologists, this anomaly isn't an error, it's a clue. A spinning parent black hole could imprint that preferred rotation on its internal space. The distribution wouldn't need to be perfectly even. It would tilt, twist, spiral. But is this a real effect or an artifact of limited data? Shamir's study looked at a few hundred galaxies, a statistically meaningful sample, but still vulnerable to selection bias. Other surveys have not found the same asymmetry. The result, while electrifying, remains unconfirmed. It stands as a testable prediction, a challenge, and a reminder that all new theories live under the microscope of skepticism. In theoretical physics, white holes are the mirror image of black holes, regions that matter and energy can exit but never enter. In the black hole cosmology model, the Big Bang itself is reinterpreted as a white hole event, the expulsion point of matter from a black hole in a parent universe. But here's the catch: we've never seen one. There are good reasons for this. White holes, if they exist, are probably short-lived and violently unstable. Their existence requires conditions we don't see in nature. Yet if our universe really began as a white hole, shouldn't there be some leftover trace, some relic, however faint? At the moment, no such evidence has been found. The model predicts that we wouldn't be able to observe the white hole directly. It would lie before our observable time, but that doesn't make it immune to critique. Critics argue that redefining unobservable phenomena is a dangerous game. The model must make falsifiable predictions or risk drifting into the realm of unfalsifiable metaphysics. The cosmic microwave background remains one of the most powerful tools in cosmology, a picture of the infant universe frozen in time. And perhaps it holds the key to resolving this debate. If our universe spun at birth, the CMB should carry that twist. We should see anisotropies, alignments, and polarization patterns that betray rotation. Indeed, some studies of the CMB, particularly those examining the so-called axis of evil, have hinted at large-scale alignments inconsistent with a purely isotropic universe. But interpretation remains murky. Are we reading deep truths in the CMB, or playing connect the dots with cosmic randomness? New missions, better data, and sharper instruments may one day tell us. To elevate black hole cosmology from hypothesis to theory, we need clear, testable predictions that differ from the standard model, repeatable, high-precision observations that support those predictions, mathematical models that don't just explain anomalies but predict them before they're observed. Gravitational wave astronomy may be the key. Upcoming missions like LISA, set to launch in the 2030s, will detect gravitational waves with unprecedented sensitivity. If echoes persist, or if we detect waves that align with internal bounce models, black hole cosmology will step out of the shadows. Similarly, quantum computing and analog gravity experiments may allow us to simulate the boundary behavior of black holes and test the holographic principle in new ways. And finally, AI-aided pattern recognition in cosmic background data may spot what human eyes miss. Black hole cosmology is not yet confirmed, but nor is it merely fantasy. It stands at the threshold between imagination and insight, compelling, controversial, and incomplete. Like all great theories before it, it asks us not just to look harder, but to look differently. It tells us that perhaps the edge of the universe is not a horizon, but a surface, not a limit, but a membrane, not a void, but the interior of something larger. And if it is correct, the proof may be drifting toward us even now, quiet ripples in the dark, waiting to be heard. Universes and the nature of existence. In black hole cosmology, our universe is not a standalone creation. It is the interior of a rotating black hole formed in another universe, a daughter universe, so to speak. This black hole collapsed under its own gravity, compressed matter and energy to extraordinary densities, and then, through mechanisms like torsion or quantum effects, triggered a bounce. That bounce didn't return to the parent universe. It unfolded inward, creating a new expanding space-time. And we live in that inward unfolding. But it doesn't end there. Just as our universe was born from a black hole, the theory suggests that black holes within our universe may do the same. Each one, if the conditions are right, may give rise to its own universe, hidden behind its event horizon, its contents forever inaccessible from our side. The result is a fractal cosmology, a universe of universes, a cosmic matryoshka doll of reality, each layer embedded in the last, each with its own physics constants and potential for complexity. This idea echoes ancient myths, the world upon the back of a turtle, standing on another turtle, and so on all the way down. But in this modern reimagining, the turtles are black holes, and they might go all the way up too. Inevitably, we're drawn to ask, where did it all begin? If our universe was born from a parent black hole, where did that parent universe come from? Was it born from yet another black hole, and that one, and that one? Does the chain go back forever? This is the cosmic equivalent of the chicken and egg problem raised to infinite dimensions. In one view, there is no first universe, just an eternal lineage of cosmic births and rebirths governed not by divine intervention or absolute beginnings, but by recurring physical processes. But in another possibility, there was a first, a primordial pavement universe, the originator of all others. Perhaps this universe didn't form from a black hole. Perhaps it formed black holes that gave rise to others. It might have been vastly simpler or incomprehensibly complex. Or maybe, just maybe, it was created on purpose. Some theorists, including futurist thinkers like John Michael Godier, have explored the notion that sufficiently advanced civilizations might gain the ability to engineer black holes and thus create universes. Think about that. If civilizations could control the parameters of these artificial black holes, mass rotation charge, they might influence the initial conditions of the resulting universe. They could, in theory, design universes optimized for stability, complexity, or even life. Like gardeners planting new gardens not on planets, but across space-time itself. And if that's the case, our universe might not just be a child, it might be an engineered offspring, tailored, fine-tuned, and set spinning by hands or minds we cannot yet imagine. This possibility reframes everything. It suggests that the fine-tuning we observe in the laws of physics, the precise values of fundamental constants that make atoms, chemistry, stars, and life possible, might not be a coincidence or a mystery. It might be a legacy. We might exist because someone or something intended us to. If so, where are they? Where are the architects, the creators, the advanced civilizations that supposedly seeded the black hole from which our universe bloomed? One answer is chilling in its logic. They've moved on. Once a civilization attains the ability to create its own universe, its own ideal cosmos, why remain in this one? Why not construct a new universe with more favorable physics, richer energy, states, fewer limits? Why not enter the very black hole they create, migrating to a realm of their own design? This becomes a potential answer to the Fermi paradox, the riddle of why we see no evidence of alien civilizations. Perhaps the most advanced beings don't leave artifacts, they leave the universe. And in their place we find silence. But not emptiness, because in that silence, life begins again. For all its physics, black hole cosmology evokes a sense of something greater. It doesn't demand belief in a God or an afterlife or a soul, but it does whisper that our universe is not alone, and neither are we. It suggests that consciousness may not be a fluke, but a pattern, an emergent behavior that arises in many universes across many horizons. It invites us to see ourselves not as cosmic accidents, but as cosmic descendants born of a long lineage of realities, each giving birth to the next, not unlike life itself. In this model, death is not an end. Collapse is not defeat. Every black hole is a potential beginning, every boundary a doorway. If black hole cosmology is true, we live inside a structure far larger, older, and more dynamic than we've ever imagined. But even if it is not, if future experiments disprove it, we've still gained something precious. We've learned that the universe is open to imagination, but tethered by reason, that it invites questions even when it withholds answers, and that every time we think we've reached the edge of knowledge, we find not a wall, but a mirror reflecting our own desire to understand. Never assume the sky is the limit. The edge of the universe might just be the start of another. And if it is, then the most human thing we can do is to keep wondering what comes next.
The universe is vast. It stretches beyond our comprehension, filled with stars, galaxies, and nebulae. But what if I told you that the universe is mostly empty space? This emptiness, far from being insignificant, holds the key to understanding the universe's structure and evolution. We often picture the universe as a dazzling tapestry of celestial objects. We envision swirling galaxies, radiant nebulae, and the twinkling of distant stars. Yet, this vision, while captivating, obscures a fundamental truth. The universe is dominated by voids. These are vast, desolate regions where matter is scarce, and darkness reigns. These voids are not merely empty spaces, they are dynamic entities shaped by the interplay of gravity, dark matter, and the expansion of the universe itself. They are cosmic laboratories where we can study the fundamental forces that govern our existence. The existence of these voids challenges our perception of the universe. It compels us to look beyond the familiar light and confront the profound implications of a cosmos defined by its emptiness. Imagine a canvas of unimaginable size. On this canvas, galaxies are scattered like brushstrokes, forming intricate patterns and vast, interconnected structures. This is the cosmic web, a tapestry of matter and energy that spans the observable universe. The cosmic web is not a random scattering of galaxies, it is a testament to the power of gravity, which drew matter together over billions of years, forming filaments, walls, and clusters of galaxies. These structures, illuminated by the light of billions of stars, trace the paths along which the universe evolved. But between these luminous strands lie the voids, vast dark expanses that dwarf the galaxies themselves. These voids are not empty in the truest sense. They contain a sparse scattering of galaxies, a thin haze of gas, and the elusive presence of dark matter. Yet compared to the bustling hubs of galactic clusters, voids are realms of profound emptiness. They are the silent spaces between the notes, shaping the cosmic symphony by their very absence. For centuries, humanity placed itself at the center of creation. We gazed upon the night sky, awestruck by the celestial dance, and assumed a privileged position in the cosmic order. But as our understanding of the universe grew, so too did our realization of its indifference to our presence. We now know that Earth is but one planet orbiting an average star in a galaxy that houses billions of its kind, and our galaxy, the Milky Way, is just one of trillions within the observable universe. This humbling realization extends to our cosmic address. Astronomical observations suggest that the Milky Way itself resides within a void, a region of space with a lower density of galaxies than the cosmic average. This void, known as the KBC void or the local hole, spans hundreds of millions of light-years. Its existence challenges our assumptions about the universe's uniformity and raises intriguing questions about our place within it. The realization that we reside within a cosmic void underscores the vastness of the universe and the relative insignificance of our own galactic neighborhood. It forces us to confront the possibility that the universe's grand design might be shaped not only by the presence of matter, but also by its absence. The universe is a symphony of forces, a delicate balance between creation and destruction, expansion and contraction. The voids, far from being passive bystanders, play a crucial role in this cosmic orchestra. They are the silent partners in a dance that has spanned billions of years, their emptiness shaping the distribution of matter and the evolution of galaxies. The voids, born from the tiniest fluctuations in the early universe, expanded over eons, driven by a force we still barely understand, dark energy. This mysterious entity, thought to permeate all of space, acts as an anti-gravity, pushing galaxies apart and stretching the very fabric of space-time. Within the voids, where matter's gravitational pull is weakest, dark energy exerts its influence most profoundly. Here, it stretches space at an accelerating rate, driving the expansion of the voids and shaping the large-scale structure of the universe. The voids are not merely empty spaces, they are the silent conductors of the cosmic orchestra, their influence shaping the music of the spheres. They are a testament to the universe's capacity for both grandeur and subtlety, a reminder that even in nothingness there is profound beauty and mystery to be found. Imagine a tapestry woven not of thread but of galaxies, billions of them, each a swirling island of stars, gas and dust. Our Milky Way is but one thread in this cosmic tapestry, a web of interconnected structures, a balance between abundance and emptiness. At grand scales, the universe resembles a three-dimensional spiderweb, its threads spun from galaxies, stretching across billions of light-years. This cosmic web is a testament to gravity's pull, drawing matter into vast, interconnected filaments and walls. These luminous strands trace the universe's evolution, marking boundaries between light and darkness. Between these filaments lie vast, desolate cosmic voids. These voids, spanning millions of light-years, are regions of profound emptiness, where galaxies are scarce and darkness reigns. They shape the universe's structure by their absence. The existence of these voids, juxtaposed against the cosmic web, challenges our understanding of the universe. The cosmos is defined by both presence and absence, by the vast silent spaces between the stars. The cosmic voids, far from being inert spaces, are dynamic entities, shaped by gravity, dark matter, and the universe's expansion. They influence the distribution of matter and the evolution of galaxies over billions of years. Imagine a vast cosmic ocean, its surface rippling with gentle waves. These waves represent subtle variations in density, remnants of the universe's tumultuous birth. Gravity amplified these variations, forming galaxies and clusters. The troughs deepened, becoming the voids that punctuate the cosmic landscape. The voids are not merely passive recipients of this cosmic flow, their gravitational pull drew material away, deepening their emptiness. This process, known as gravitational evacuation, amplified the contrast. The voids influenced the evolution of galaxies. Galaxies' paths were shaped by the gravitational tug of surrounding matter. This interplay influenced galaxy collisions and star formation. The cosmic voids played a subtle yet profound role in sculpting the universe. They were active participants in the cosmic dance woven into space-time. To understand cosmic voids, we must journey back to the universe's infancy, to a fraction of a second after the Big Bang. The universe was an inferno of energy, a seething cauldron of particles and radiation. Quantum fluctuations created tiny density variations, tipping the scales in favor of gravity, setting in motion the formation of galaxies and voids. These voids are echoes of the Big Bang, remnants of the universe's earliest moments. The vastness of cosmic voids evolves over billions of years, adding complexity to the cosmic tapestry. Gravity draws matter together, but dark energy, a cosmic anti-gravity, shapes the universe's destiny. Dark energy permeates space, driving the accelerated expansion of the universe. In dense galaxy clusters, gravity binds structures together. In cosmic voids, dark energy reigns supreme. As the universe expands, voids stretch wider. This expansion counteracts gravity, shaping the universe's structure. Dark energy accelerates space expansion, pushing galaxies apart. Cosmic repulsion isolates galaxies, suggesting a future dominated by voids. Voids are dynamic, shaped by gravity, dark matter, and dark energy. They offer clues to dark energy and the cosmos's fate. Our Milky Way galaxy, nestled within the local group, resides in the KBC void, a stark reminder of the universe's penchant for emptiness. It dismantles the notion of a uniformly populated cosmos, replacing it with vast structures and immense voids. Our presence within a void offers a unique perspective. It is a universe that constantly challenges our perceptions. Within the vast cosmic tapestry, where galaxies cluster in luminous strands and filaments, the Bootes void stands apart, a region of astonishing emptiness that stretches across 330 million light-years, dwarfing all other known voids in scale. Discovered in 1981 by astronomer Robert Kirshner and his team, this cosmic abyss, located some 700 million light-years from Earth in the constellation of Bootes, challenges our understanding of the universe's structure and the forces that govern it. Imagine a sphere so vast that if our Milky Way galaxy were a grain of sand, the Bootes void would be the size of the Earth. Within this immense volume, one might expect to find thousands upon thousands of galaxies, swirling islands of light and matter, each home to billions of stars. Yet, observations reveal a starkly different reality. Only a few dozen galaxies, a paltry 60 or so, have been detected within the Bootes void, clustered in a peculiar tube-like structure that pierces its heart. This profound emptiness, a cosmic desert in a universe teeming with galaxies, poses a fundamental question: why is the Bootes void so empty? What forces conspired to create this immense region where matter seems to have been banished, leaving behind a cosmic echo chamber where the whispers of the early universe may still resonate? The Bootes void is not merely an anomaly, it's a cosmic enigma, a challenge to our understanding of how the universe evolved from a nearly uniform sea of energy into the intricate tapestry of galaxies, clusters, and voids we observe today. It beckons us to explore the interplay of gravity, dark matter, and dark energy, those unseen sculptors of the cosmos, and to unravel the mysteries that lie hidden within its depths. Within the vast cosmic tapestry where galaxies cluster in luminous strands and filaments, the Bootes void stands apart, a region of astonishing emptiness that stretches across 330 million light-years, dwarfing all other known voids in scale. Discovered in 1981 by astronomer Robert Kirshner and his team, this cosmic abyss, located some 700 million light-years from Earth in the constellation of Bootes, challenges our understanding of the universe's structure and the forces that govern it. The Bootes void's stark emptiness contrasts with the surrounding cosmic landscape. It's encircled by massive structures like the Great Wall, the Coma supercluster, and the Hercules supercluster. These structures highlight the Bootes void's anomalous nature. It's as if the universe carved out this immense void. Astronomers propose it formed from low-density fluctuations or merging smaller voids. The Bootes void's scale and shape suggest other, less understood forces at play. The Bootes void is a dynamic environment shaped by gravity, dark matter, and dark energy. These forces shape the cosmos, driving galaxy evolution. Gravity forms stars, galaxies, and clusters. In cosmic voids, gravity's grip weakens. Dark matter forms a scaffolding, holding galaxies together. In the Bootes void, dark matter distribution holds clues. Less dark matter means weaker gravity, hampering galaxy formation. Dark energy drives cosmic expansion. It pushes galaxies apart, stretching spacetime. This cosmic repulsion shapes the Bootes void. As the universe expands, so does the void. This expansion counteracts gravity, shaping the universe. The Bootes void, with its sparse population of galaxies and vast stretches of emptiness, offers a unique window into the early universe, a cosmic time capsule preserving the conditions that prevailed billions of years ago. Unlike galaxies where stars are born and die, enriching the interstellar medium with heavy elements or galaxy clusters, where collisions and mergers reshape galaxies over time, voids remain relatively pristine, their contents largely unchanged since the universe's infancy. This pristine environment makes the Bootes void an ideal laboratory for studying the fundamental properties of the universe. By observing the few galaxies that do reside within the void, astronomers can glean insights into the processes of galaxy formation and evolution, in the absence of significant gravitational interactions with neighboring galaxies. Furthermore, the void's vast emptiness provides a unique opportunity to study the cosmic microwave background radiation, the faint afterglow of the Big Bang, with minimal interference from intervening matter. This radiation, a fossil from the universe's earliest moments, carries information about the universe's age, composition, and evolution. By studying the cosmic microwave background radiation within the Boots void, astronomers can probe the conditions that prevailed in the early universe, testing cosmological models and refining our understanding of the universe's origins. The Boots void, therefore, is not merely a region of emptiness, it's a cosmic treasure trove, holding clues to the universe's deepest secrets. It's a reminder that even in the absence of light and matter there is much to be learned, much to be discovered about the nature of the cosmos and our place within it. The Boots void, with its sparse population of galaxies, offers a unique window into the early universe, a cosmic time capsule preserving conditions from billions of years ago. This pristine environment makes the Boots void an ideal laboratory for studying the universe. It's a cosmic treasure trove, holding clues to the universe's deepest secrets. The Boots void, with its stark emptiness, contrasts with bustling galaxy clusters. It challenges our perceptions, reminding us the cosmos is a tapestry of matter and absence. Voids shape the universe's structure, influencing galaxy formation. They are silent partners in a cosmic dance spanning billions of years. Even in emptiness, profound mysteries await. Cosmic voids, vast expanses of emptiness, were sown in the universe's infancy, mere fractions of a second after the Big Bang. The universe was a turbulent ocean, roiled by quantum fluctuations, tiny variations in energy density. Imagine a vast, dark ocean, its surface constantly shifting, rippling with waves. These fluctuations represented regions where energy density was slightly higher or lower. These fluctuations set in motion events shaping the universe's matter distribution. Regions with increased energy density had a stronger gravitational pull. These denser regions drew in more matter, amplifying density contrast. Over eons, these regions became the seeds of galaxies and clusters. Regions with lower energy densities experienced weaker gravitational pull. These regions expanded outward, their matter density thinning. The seeds of abundance and emptiness were sown in the universe's first moments. As the universe expanded and cooled after the Big Bang, gravity shaped the cosmic web, drawing matter into stars and galaxies, and creating vast cosmic voids. Gravity, the universe's sculptor and excavator. The formation and evolution of cosmic voids were not solely governed by ordinary matter. Dark matter played a crucial role in shaping the universe's large-scale structure. Unlike ordinary matter, dark matter does not interact with light. Its presence is inferred through gravitational effects on visible matter. Dark matter forms a vast, invisible halo around galaxies and permeates the cosmic web. As gravity diligently sculpted the universe's large-scale structure, another force, a cosmic anti-gravity known as dark energy, was subtly at play, shaping the universe's destiny on grand scales. This enigmatic force, thought to permeate all of space, acts as a counterpoint to gravity's pull, driving the accelerated expansion of the universe. In the dense regions of galaxy clusters, gravity's influence still holds sway, binding these structures together against the cosmic flow. However, within the vast expanses of cosmic voids, where matter is scarce, dark energy's influence reigns supreme. As the universe expands, the voids expand along with it, their emptiness stretching ever wider. This expansion is not merely a passive stretching, it is an active force, counteracting gravity's pull and shaping the large-scale structure of the universe. Within the voids, where gravity's grip is weakest, dark energy accelerates the expansion of space, pushing galaxies away from each other and driving the voids to grow ever larger. This cosmic repulsion, subtle yet relentless, has profound implications for the universe's fate, suggesting a future where voids dominate and galaxies become increasingly isolated, islands in a vast, ever-expanding sea of darkness. Cosmic voids, far from desolate, are invaluable laboratories. They offer insights into the early universe, dark matter, and dark energy. Studying the cosmic microwave background reveals the universe's age, composition, and evolution. Voids also help map dark matter and study dark energy's influence on cosmic scales. Galaxies in voids offer clues about galaxy formation in low-density environments. As the universe continues its relentless expansion, driven by the enigmatic force of dark energy, cosmic voids will dominate the cosmic landscape. The cosmic web will stretch, isolating galaxy clusters and driving galaxies further apart. Voids will expand and merge, becoming vaster and emptier. Galaxies will drift apart, becoming isolated islands in a sea of darkness. The future of the universe is a future dominated by voids. The discovery of vast cosmic voids like the Boots void presents a profound paradox. How can a universe governed by gravity manifest such extreme density variations? The universe revels in contrasts. It is a realm where the small and vast coexist. This duality is a testament to the universe's complexity. The Bootes void challenges the cosmological principle, which asserts the universe is homogeneous and isotropic. This principle suggests no preferred locations or directions in the universe, yet vast voids like Bootes seem to contradict this. Are these voids statistical anomalies or signs of a needed revision? Section 3. The limits of uniformity. The challenge posed by cosmic voids to the cosmological principle highlights a fundamental aspect of scientific inquiry: the constant need to refine our understanding in the face of new observations and discoveries. The cosmological principle, though a powerful tool for understanding the universe, is ultimately based on observations and assumptions that are subject to revision as our knowledge expands. The concept of homogeneity, as applied to the universe, is not absolute but rather scale-dependent. On smaller scales, such as those of galaxies and galaxy clusters, the universe is clearly inhomogeneous. Stars cluster into galaxies, galaxies clump together into clusters, and clusters group into superclusters, forming the intricate web-like structure we observe. However, as we zoom out to larger and larger scales encompassing billions of light-years, the universe appears to become smoother, with the variations in density averaging out. The cosmic microwave background radiation, for example, exhibits remarkable uniformity in all directions, suggesting that the early universe, at least on very large scales, was remarkably homogeneous. The discovery of cosmic voids, however, suggests that this averaging process may not be perfect, and that significant inhomogeneities can persist even on the largest scales we can observe. The Bootes void, for instance, spans a significant fraction of the observable universe, challenging the notion of a completely homogeneous cosmos. Section 4. Embracing the paradox. The tension between cosmic voids and the cosmological principle deepens our understanding of the universe. It compels us to refine our models and explore new research avenues. Science progresses through resolving paradoxes and reconciling contradictions. Cosmic voids challenge us to embark on a journey of discovery. They may represent a breakdown of the cosmological principle on large scales. Perhaps the universe exhibits large-scale density variations. Our understanding of the cosmological principle may need refinement. Homogeneity might imply statistical uniformity, allowing rare fluctuations. Cosmic voids compel us to re-evaluate our assumptions. The cosmos is vast, complex, and full of mysteries. Section 5. Voids, beacons in the cosmic sea. Cosmic voids, once thought insignificant, are now seen as integral to the universe's structure and evolution. They offer insights into dark matter, dark energy, and the universe's expansion. Studying voids helps us understand the universe's early history and the formation of stars and galaxies. Voids illuminate the universe's deepest secrets, guiding us toward a more complete understanding of the cosmos. The Boots void, in its vastness and emptiness, invites speculation. Could this cosmic desert harbor the remnants of advanced civilizations? Imagine a civilization capable of harnessing the energy of entire stars. Such a civilization might have left subtle traces within the Boots void. Perhaps the void's sparse galaxies are the remains of a once thriving galactic neighborhood. The Booties void, in its silence and emptiness, might hold more than just the echoes of vanished civilizations. It could harbor messages, subtle patterns imprinted on the fabric of space-time, waiting to be deciphered by those who know how to listen. Imagine a civilization seeking to communicate across the vast gulfs of interstellar space, not with radio waves or laser pulses, but with the very structure of the universe itself. Such a civilization might have chosen the Booties void, a region of relative calm and stability, as a cosmic canvas upon which to inscribe their messages. These messages might take the form of subtle variations in the density of dark matter, patterns etched into the cosmic microwave background radiation, or even slight anomalies in the expansion rate of the void itself. Deciphering such messages would require not only advanced technology, but also a fundamental shift in our understanding of the universe and the possibilities of communication. The very emptiness of the Bootes void could itself be a message, a deliberate act of cosmic art designed to attract attention and spark curiosity. Perhaps the void is a beacon, a cosmic signpost left by a long-gone civilization, inviting others to unravel its mysteries and uncover the knowledge it holds. The Booties void, with its vast scale and low matter density, presents a unique environment for cosmic engineering projects of unimaginable scope. Could this seemingly empty region of space be a testing ground for advanced technologies, a cosmic laboratory where civilizations far more advanced than our own experiment with the fundamental laws of physics? Imagine a civilization capable of manipulating dark matter and dark energy, the invisible forces that shape the universe's destiny. The Boots void might be a playground for advanced civilizations, pushing the limits of technology and cosmic engineering. Beyond the Fermi paradox, the void's silence, the Bootes void's profound emptiness raises intriguing questions about the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life and the lack of observational evidence for it. If the universe is teeming with life, as some theories suggest, then why haven't we encountered any signs of it, particularly in a region as vast and seemingly untouched as the Bootes void? One possibility is that advanced civilizations, rather than broadcasting their presence, choose to remain silent, concealing themselves from potential threats or simply observing the universe without interfering. The Bootes void, with its isolation and lack of readily observable resources, might be an ideal location for such a civilization to remain hidden, observing the universe from the shadows. Another possibility is that advanced civilizations are transient, their lifespans limited by resource depletion, internal conflicts, or technological singularity events that propel them beyond our comprehension. The Bootes void, in its vastness and age, might have hosted numerous civilizations throughout its history, their rise and fall leaving behind only faint traces, if any. The void's silence, therefore, might not be an indication of the absence of life but rather a consequence of the vastness of time and space, the fleeting nature of civilizations, and the possibility that advanced intelligence chooses to remain hidden from view. The Bootes void, in its enigmatic emptiness, serves as a powerful reminder of the universe's vastness, its mysteries, and the limitations of our current understanding. It challenges us to confront the unknown, to embrace speculation and imagination, and to acknowledge that our current scientific framework, though impressive, is likely just a glimpse into a far grander and more complex reality. The void's emptiness, far from being a sterile wasteland, is pregnant with possibilities. It invites us to explore the boundaries of our imagination, to consider the existence of advanced civilizations, cosmic engineering projects, and perhaps even realities beyond our current comprehension. The Boot's void, in its silence, speaks volumes. It whispers of the universe's boundless capacity for both creation and negation, for both abundance and emptiness. It reminds us that the cosmos is not a static, unchanging backdrop, but rather a dynamic, evolving entity, full of surprises and wonders waiting to be discovered. As we continue to explore the universe, peering deeper into the cosmos with ever more powerful telescopes and instruments, we can expect to uncover more mysteries, more anomalies that challenge our current understanding. The Booty's void, in its enigmatic silence, stands as a beacon, a reminder that the universe is a vast, complex, and ultimately unknowable entity, forever unfolding its mysteries before us. The Boot's void, a cosmic abyss stretching across hundreds of millions of light-years, stands as a testament to the universe's capacity for both grandeur and enigma. Its profound emptiness, far from being a sterile wasteland, has captivated astronomers and laypeople alike, sparking curiosity and igniting the flames of speculation. We are drawn to the void's mystery, to the possibility that it holds secrets beyond our current comprehension. Could this vast expanse of emptiness harbor the remnants of advanced civilizations, the echoes of cosmic engineering projects, or perhaps even glimpses into dimensions beyond our own? The void's allure lies not only in its potential to upend our understanding of the universe but also in its stark beauty. In a cosmos filled with the dazzling light of trillions of stars, the void's darkness offers a different kind of splendor, a reminder that absence can be as powerful as presence, silence as profound as sound. The Boot's void beckons us to contemplate the universe's extremes, to journey beyond the familiar comfort of stars and galaxies, and confront the awe-inspiring scale of cosmic emptiness. It is a journey that challenges our perceptions, stretches the limits of our imagination, and ultimately deepens our appreciation for the cosmos and our place within it. The discovery of cosmic voids, particularly structures as immense as the Booty's void, has profoundly altered our understanding of the universe. It has challenged our assumptions about the cosmos's uniformity, the distribution of matter, and the role of gravity in shaping the large-scale structure we observe. We once envisioned a universe relatively evenly populated with galaxies, a cosmic sea of stars stretching infinitely in all directions. However, the existence of voids has shattered this paradigm, revealing a cosmos far more complex and intricate than we could have imagined. The universe, we now know, is not a smooth, homogeneous expanse, but rather a tapestry woven from both matter and its absence, a delicate balance between the luminous threads of galaxies, clusters, and filaments, and the vast, dark voids that lie between. This realization has forced us to re-evaluate the role of gravity in shaping the cosmos. Gravity, once thought to be solely responsible for drawing matter together, is now understood to play a more nuanced role, both assembling matter into luminous structures and simultaneously carving out vast expanses of emptiness. The discovery of voids has ushered in a new era of cosmological research, one that embraces the universe's complexity and seeks to understand the interplay of gravity, dark matter, dark energy, and the expansion of the universe itself in shaping the cosmos we observe. The exploration of cosmic voids is akin to setting sail into uncharted waters, leaving behind the familiar shores of galaxies and clusters to venture into a realm where emptiness reigns supreme. It is a journey into the universe's unknown, a quest to unravel the mysteries that lie hidden in the darkness. Just as early explorers set sail across vast oceans, driven by curiosity and a thirst for discovery, astronomers are now peering into the depths of cosmic voids, using ever more powerful telescopes and instruments to chart their contours, analyze their contents, and unravel their secrets. These explorations have already yielded remarkable insights. By studying the few galaxies that do reside within voids, astronomers are gaining a better understanding of galaxy formation and evolution in low-density environments, where gravitational interactions with neighboring galaxies are minimal. The study of voids has also provided crucial insights into the nature of dark matter and dark energy, the invisible forces that shape the universe's destiny. By analyzing the motion of galaxies within and around voids, astronomers can map the gravitational influence of dark matter, while the expansion rate of voids themselves offers a sensitive probe of dark energy's enigmatic properties. The exploration of cosmic voids is still in its infancy, but it has already revolutionized our understanding of the universe. As we continue to push the boundaries of observation and theory, we can expect even more remarkable discoveries from these seemingly empty regions of space. The study of cosmic voids is a profound quest to understand our place in the universe. By exploring the universe's extremes, we gain a deeper appreciation for its intricate workings. The quest for cosmic understanding is a journey without end, a continuous process of exploration and discovery. Cosmic voids remind us that the universe is far grander and more wondrous than we can imagine. The existence of cosmic voids, far from diminishing our place in the universe, underscores the remarkable interconnectedness of all things. We are not isolated observers, looking out upon a vast and indifferent cosmos, but rather active participants in a cosmic dance that has spanned billions of years. The atoms that make up our bodies, the air we breathe, the very earth beneath our feet, all were forged in the hearts of stars that lived and died long ago, their remnants scattered across the cosmos by supernova explosions, eventually coalescing into new stars, planets, and ultimately, life itself. The cosmic web, with its filaments, walls, and voids, is a testament to this interconnectedness, a visible reminder that the universe is not a collection of isolated objects but rather a dynamic, evolving system, where every part is linked to every other. Our presence within the KBC void, a region of relative emptiness within the cosmic web, is a reminder that even in the universe's quietest corners, the echoes of creation resonate. We are a product of the universe's grand evolution, a testament to its capacity for both complexity and beauty. The Booty's void, in its vastness and emptiness, serves as a powerful symbol of the universe's boundless capacity for wonder and possibility. It is a blank canvas upon which we can project our hopes, our fears, and our wildest imaginations. The void's emptiness, far from being a source of despair, can be seen as an invitation to explore, to dream, and to imagine possibilities beyond the confines of our current understanding. It reminds us that the universe is far grander, more mysterious, and more awe-inspiring than we can possibly comprehend. Could the void harbor life as we've never known it, existing in forms and dimensions beyond our current imagination? Could it be a realm where the laws of physics as we understand them break down, giving rise to phenomena that challenge our very notions of reality? The possibilities are as limitless as the void itself. The Buddhist void, in its silence, speaks volumes. It whispers of the universe's infinite potential, its capacity for both the familiar and the unknown, the mundane and the extraordinary. It is a reminder that the cosmos is a realm of endless wonder, a place where discovery never ceases and where the boundaries of human understanding are constantly being pushed. The Booty's void, a cosmic abyss, stands as a silent invitation to explore the universe's grandest mysteries. Its profound emptiness beckons us to venture beyond the familiar, to embrace the unknown. The void's silence whispers possibility, challenging our understanding and inspiring our imagination. It reminds us that the universe is more than the sum of its visible parts. Within its darkest corners lie secrets waiting to be uncovered. The Booty's void stands as a beacon, a reminder of the universe's vast, complex mystery.